Okay, in this video, we're going to derive matching equations for the inner and outer solution, and then we're going to use them to determine the coefficients that were left undetermined in the previous example. Right, so we said in this boundary layer type of problems, you're going to have a boundary layer, say at this end, so we called that one the inner region, and then there is the outer region, which is going to be at the other end, and then there is this region which is called the intermediate region. In the boundary layer, we introduced a scaled variable xi. In the outer region, we use the original variable x, and in the problem that we worked on, the relationship was x is equal to epsilon times xi. So the equations are derived from the fact that in this intermediate region here, the two solutions must match. So that means if you take the inner solution and take the limit as xi goes to infinity, this must be equal to the outer solution in the limit x goes to 0. Right, so this translates as follows. So limit as xi goes to infinity of big Y must be equal to limit as x goes to 0 of small y. Now, of course, we did an expansion of big Y, so that's y naught epsilon y1 epsilon squared y2, etc. And then on the other hand, we have got this one, which we wrote as y naught epsilon y1 epsilon squared y2, etc. By the way, this equation here is due to Prandtl. Now so the thing is, on the left hand side here, we have got an equation in terms of xi. On the right hand side, we've got an equation in terms of x. So what we're going to do is we're going to write the equation on the right hand side in terms of xi, so that both sides are expressed based on the same variable. So since x is equals to epsilon times xi, so when x is 0, xi is 0. As x goes to 0, xi goes to 0 as well. So we're going to expand these ones in terms of Taylor series in terms of xi. So for instance, y naught of x, we're going to write as y naught of epsilon times xi. So epsilon times xi. Then expand this about xi equals to 0. It's going to be y naught at 0 plus epsilon xi y naught prime at 0 plus epsilon squared xi squared over 2 y double prime at 0, etc. Okay, so that's going to be y naught, and then same thing with y1 of x is going to be y1 of epsilon xi. It's going to be y1 at 0 plus xi y1 prime, etc. Now remember, this one is multiplied by epsilon, and then same thing for y2. So when all this has been done, then this right hand side is going to look as follows. We're going to have the terms at order 0 is just going to be y0 at 0. Then the terms at order epsilon, we are going to have xi y0 prime at 0 plus y1 at 0. And then the terms at order epsilon squared, we're going to have 1/2 xi squared y0 double prime, and then there's going to be xi y1 prime, and then it's going to be y2 at 0, etc. So using these, we can derive the following three equations which we're going to use for matching. So at order 1, we're going to have that the limit of y0 as xi goes to infinity must be equal to y0 at 0, which is this one. Then at order epsilon, we're going to have that the limit of y1 as xi goes to 0 must be equal to xi y0 prime at 0 plus y1 at 0. And then at order epsilon squared, we must have that the limit of y2 as xi goes to infinity is going to be equal to 1/2 xi squared y0 double prime plus xi y1 prime at 0 plus y2 at 0. Okay, so for us, these are going to be good enough. Actually, we're just going to use these two here. Now, remember in the problem that we did earlier, which is this one, y at 0 is 0, y when x is 1 is 1. So for the outer solution, we got that y0 is going to be e to the 1 minus x. y1 is 1/2 y1 is 1/2 1 minus x e to the power 1 minus x. Then the inner solution, we got that y0 is going to be a into 1 minus e to the minus 2 xi. y1 we got to be d e to the minus 2 xi minus 1 minus a xi 1 plus e to the minus 2 xi. Now, so of course we did say that these constants we are going to find using these matching equations, right? So if we start at order 1, so at order 1, the equation we have is limit of y0 as xi goes to infinity must be equal to y0 at 0. the left hand side we've got the inner variable y, right hand side we've got the outer variable y. Now if we look at this, as xi goes to infinity, that thing is going to give us a. And then this one, if we plug in 0, that thing is going to give us e. And so a is equal to e. Then at order epsilon, we have got limit y1 as xi goes to infinity. That is going to be xi times y naught prime evaluated at 0 plus y1. Now, so this thing as xi goes to infinity is going to be negative d from the first term minus a xi from the second term. Okay, so that's on the left hand side. On the right hand side, derivative of y naught is the negative of this. Then if we plug in 0, that's going to give us xi times negative e. Then y1, if we plug in 0 here, is going to give us e over 2. Okay, now remember a has already been determined. A is e, so actually on the left hand side got minus d minus e xi is equal to minus e xi plus e over 2, and these two are already matching, which is a good indication. And then from here, this is telling us that d is actually negative e over 2. Then we have got d, and we have got a. So we can now rewrite the inner solution exactly. So we're going to have y naught is equal to e into 1 minus e to the minus 2xi. And then on the other hand, y1 is going to be equal to e over 2, 1 minus e to the minus 2xi minus exi 1 plus e to the minus 2xi. And so our solutions are fully determined now. However, that's not the end. The next thing we need to do is to find a uniformly valid solution or composite solution. So we derive this using the following equation. So y uniform is going to be equal to y inner plus y outer minus y common. Y common is always going to be given by the terms we got during the matching at each order. Okay, so for instance, at order epsilon, the y common term is going to be this one. Okay, then at order 1, the y common term is going to be e. So that means we can now derive the leading order uniform expansion. Okay, so that is the expansion at order 1. So y uniform is going to be equal to y naught, which is e to the 1 minus x. That's the outer solution. then this is going to be plus the inner solution here. We're going to write everything now in terms of x. So e brackets 1 minus e to the minus 2x over epsilon. Remember that xi is x over epsilon. Okay, then take away the common term, which is e. Okay, so when we do that, then these two terms are going to cancel out. So that's this term and this term there. So ultimately, our uniformly valid solution at order 1 is going to be e to the 1 minus x minus e to the 1 minus 2x over epsilon. Okay, if we do the same thing at order 1, we are going to find the following expression. Okay, so at order epsilon, the y uniform is going to be equal to brackets 1 plus epsilon over 2 into 1 minus x e to the 1 minus x. So these are the terms from the outer solution, and then for the terms arising from the inner solution, we are going to have 1 plus epsilon over 2 plus x, so writing everything in terms of x, e to the 1 minus 2x over epsilon. Okay, in a subsequent video, we are actually going to see plots of how these two compare with each other and also compare with the exact solution. Yeah, so we're going to end that one here.